So what we just discussed is that the two most important relations are dg is vdp minus sdt and dA is minus sdt plus pdv. And then, so according to our just discussion which we just had, we said that the two most important quantities are dA and dg, and the conditions for spontaneity and equilibrium for these two thermodynamic functions are given by dA is minus sdt minus pdv and dg is minus sdt plus vdp. So you can easily figure out that for dA the conditions to be kept constant are temperature and volume, then dt and dv will be 0, and then dA equal to 0 at constant temperature volume, or dA at constant or dg at constant pressure and temperature similarly can be less than equal to 0. So these are the natural choice for the conditions for equilibrium and spontaneity, which we'll be frequently using. Now let us focus on the Gibbs free energy change only. So we'll start with this equation, and we can first ask this question: what is the derivative of the Gibbs free energy with respect to, say, temperature and pressure? Because just like we formulated the Maxwell relations, we can, in the similar spirit, write del G, del, say first we are taking the variation of Gibbs free energy with temperature. So then we'll just use del G del T at constant pressure. That will be nothing but equal to S. Now we are using only the equilibrium sign here because we are only considering the variation, keeping the system at equilibrium. So this will be equal sign. Now what will be the curve for this? If I plot G versus T, how the curves look like? Now remember, S is entropy, and entropy is a positive quantity, which means del G del Tp is always a negative quantity, or del G del Tp, it decreases as we increase the temperature, because del G del Tp is the slope. So Gibbs free energy decreases with increase in temperature. Now the decrease will be more for a gas. It will be much less for liquids and solid. So if this is gas, let me draw it once again. Suppose this is for gas, and then the liquid will decay a little bit and the solid will decay even less. So this is the curve for liquid and this is the curve for solid. Now you see that this decay is linear in the sense that as long as the slope is constant, which is the entropy of the solid or the liquid or the gas, then the slope will of course be linear. However, we'll see that if there is a phase transition, if we keep on increasing the temperature and suppose there is a all of a sudden phase transition, then we'll have breaks in these curves. So the curve will look like something like this and like this, which we'll discuss when we talk about phase transition. Similarly, you can ask a similar question like what will be the variation of the Gibbs free energy with pressure, and you can easily figure out from this equation that it is nothing but V. Now usually people do not plot V, people divide both sides by the Avogadro number, or the number of moles. So then what you will get is this will be nothing but your molar volume, and this will be the molar Gibbs free energy. Now, if we plot the change in Gibbs free energy as a function of temperature, pressure, how it will look like. Now, it is actually dependent on the molar volume. So, if I increase the pressure, how the volume will change. So for gas, the change in volume will be something like that. We'll discuss why the curve looks like this. And for liquids and solids, the volume will be like this. The change will be like this. So this is for gas. This is for liquid. For solid, the curve will be more or less flat because the change is very minimal. Because the molar volumes of solid or volume of a solid does not change too much if I apply the pressure. Now, you can easily figure out from these equations that we can get a feeling of how Gibbs free energy is changing with respect to pressure and temperature. But let us first discuss, before discussing why their curves are like this, let us first discuss another important quantity, which is not the Gibbs free energy, but the Gibbs free energy divided by temperature, how that quantity change. Now let us consider how this quantity, Gibbs free energy divided by T, changes with temperature. For that, we can calculate this quantity, what is the derivative of G by T, or the partial derivative of G by T with respect to temperature, keeping the pressure constant. So let us use the chain rule of differentiation. So if we take first the differential with respect to differential of G, so the first term will be 1 over T del G del T P, and the second term will be the differential of 1 over T, so that will be G over T square. Now we know that, already we showed it, del G del T P is nothing but minus S. But if you use minus S here, we will not get a very useful relationship because the G is sitting here. So we can write the minus S again in terms of G. Now from definition, G is H minus Ts. So G minus H is minus Ts. So minus S is G minus H divided by T. So it is G minus H divided by T. Now if you put this in this equation, what we get is 1 over T. We can take 1 over T common, and then I'll have del G del T P minus G over T, because we have taken 1 over T common here. And then we get for del G del T P, which is minus S, we'll just write G minus H by T minus G by T, and we took 1 over T common. Then this G by T factor will cancel out, and we'll be left with minus H by T square. So this equation, that del T of G by T is minus H by T square, is a very, very important relationship, because here we see that we can directly measure the change in Gibbs free energy divided by temperature with respect to temperature and connect it to the enthalpy. Now whenever we have a phase change, we can actually use this equation, because during the phase change we can have usually the pressure and temperature are kept constant. So you can have, for example, if we are considering a vaporization of water, then the associated heat change will be nothing but, since it is at constant pressure, QP will be equivalent to H, and then we'll be considering only H of the fusion. Now, instead of H of the fusion, what we need now is delta H of, say, fusion or vaporization or sublimation, whichever process it is. So how do you write it in terms of delta H? Now we can start from the same equation and we can write that, well, I can actually use, say, if we ask this question, what will be del T of delta G by T? We can have it rewrite it in very nice way, that we can write, okay, what is delta G? Delta G is nothing but G2 minus G1. So we can just write it as G2 divided by T minus G1 divided by T, and we can use the same expression, and then what we will discover, this is nothing but del minus H2 divided by T square minus H1 divided by T square. So which is nothing but minus 1 over T square into delta H. So we can get another useful relation, which is del of delta G by T del T is minus del H by T square. So either form is known as Gibbs Helmholtz equation. So this will be very important when we discuss phase transition. Now let us discuss why the curves of G versus P or G versus T looked like the way we drew. Now remember, for a finite change, which is delta G, we can always write, remember that G is a state function, dg between state 1 and 2, and then if we consider, say, a constant temperature process, so there it will be nothing but VdP, because dg was VdP minus SdT. So we'll have volume 1 to 2, and again if we are considering, say, a molar volume, we can use either the sign M or we can use G bar, whichever is fine. We're just dividing both sides by the number of moles, and then we get the equation for the molar volume. Now if the molar volume is constant, which will be the situation for, say, solids, then I'll have a very simplified integration, which is nothing but molar volume times the final pressure minus initial pressure. So this will be true only for solids. And if you now plot how the delta G looks like, so the molar volume will be more or less constant, and if I multiply it by P2 minus P1, so the delta G will be nothing but the area under this curve. However, in reality, if you apply more and more pressure, the molar volume will actually decrease, and there will be some error introduced in this, because we are basically including this area which we should not have included. Now similarly, if it's a gas, so then we can actually use the ideal gas equation, where we have to write this volume in terms of pressure using nRT by V, but it is molar volume, so it will be RT by V, and since the temperature is constant, you can take it out of the integral. So I'll have here 1 going to state 2, then the expression will be RT ln P2 by P1, and how the curve will look like. So it's a logarithmic plot, and you know how the PV diagram looks like, but instead of PV we are drawing here as a VP diagram. Keep that in mind. And then we have like this, because according to Boyle's law, P is proportional to V, or we could write actually V proportional to P. So this is the curve, and if we take to one lower limit, which is P1, and one upper limit, which is P2, then the Gibbs free energy will be nothing but area under the curve, or the change in Gibbs free energy will be nothing but area under this curve. And then you can always argue that when we vary the temperature, when we do the other quantity, which we just discussed for gas, remember that it was we had an equation like del, if you just go back and check this thing, your del G del P, the variation of Gibbs free energy with respect to, say, with respect to pressure at constant temperature, was V. Now think about it, how the curve will look like for a gas. We draw a curve like this. Now this is coming because here we are plotting G versus P. Now as you increase the P, now the V is also changing. The slope of the curve is V here. So as I'm changing the pressure, initially I had a very high slope. Why? Because at low pressure the volume was more, at high pressure the volume was less. So that's why the slope is changing, slope of the curve. However, for solids and liquids, the change in the volume with respect to pressure is not that much. Overall, remember that V is a positive quantity, that's why you have a positive slope, but the slope itself is changing. So that's why I had a curve like this, and for solids it almost doesn't change. However, for gas, it changes a lot because gases are more compressible than solids and liquids, and that's why this curve looks like this, where this at slope at any point is given by the volume, but the volume itself actually decreases as we increase the pressure. So the slope itself is decreases as we are increasing the pressure. So you could actually plot the variation of Gibbs free energy as a function of pressure and temperature together and get something like a surface plot, which we also plotted for pressure, volume, temperature when they're all varying together. And you can get a surface just like we did for pressure, volume, temperature for ideal gas. And similarly, you could generate a surface, or you could plot the G versus P and T together. And this is a very interesting surface. You can have a look at it. It is given in the book by Peter Atkins, which is referred for this course. Now we'll conclude our discussion for this part here, and before that, let us summarize what we discussed in this entire section, which where we discussed about spontaneity and equilibrium. So we started from a very fundamental equation that TdS must be greater than or equal to d cross q, starting from the argument that ds is equivalent to d cross q reversible, and the reversible heat change is either the same of the heat change of the process if the process is reversible, or it will be more than the heat change of the process, which is d cross q, if the process is not reversible. And then starting from this fundamental equation, we built up many other equations in terms of du, dh, dA and dG, and we showed that each of this equation will give rise to a condition for spontaneity or equilibrium, but the spontaneity is given by the less than sign and the equilibrium is given by the equal to sign, but the conditions are very, very different. For du it was constant volume temperature it was constant volume and entropy, because du was TdS minus PdV. For dH it was constant pressure and entropy, because it was TdS plus VdP, and for dA we had constant volume and temperature, and dG we had constant pressure and temperature. And since pressure, volume, temperature are three more of fundamental parameters which we can keep constant or change as our will, so we often either change the temperature and the volume or the pressure and the temperature. So the natural quantity to look at is either dA or dG, and we argued that in most of the cases we keep the pressure constant, which means this is the most useful relationship which we will be using. Now in the next lecture we'll discuss, we'll just build up from our discussion on this particular aspect, and then we'll be talking about phase transition. And then first we'll talk about only one component, in the sense that only one pure substance is present, for example say water, and we'll discuss how the free energy or the Gibbs free energy at constant pressure is changing if we change the temperature, for example. And we know that water, if we just heat ice, it will first melt into water, and then over a large range of 0 degrees centigrade to 100 degrees centigrade, it will be liquid water, and then it will boil and form water vapor. So that is the gaseous phase, and we'll talk about it. How does it look like in an energy diagram, in an equivalent energy diagram, and how what happens when how the curve looks like when we have a phase transition, meaning when at some point when we are having say ice to water transition, how the curves look like. Of course, I mean, in those curves we will have a discontinuity, as is obvious when we are discussing that the change in Gibbs free energy as a function of temperature, or say change in Gibbs free energy as a function of pressure. We discussed that this is the pressure curve, and we could discuss the temperature curve also like this. And then remember that we said that the curves will look like this, and suppose this is for a curve of liquid and this is suppose curve for a solid. And then if you have a liquid to solid transition, then the curve will first change like this, and then eventually it will change much more slowly. So the curve will be something like this. It will first come like this, and then it will change slowly. Something like that will happen. So we'll discuss how to represent this thing, and where this temperature will be called as, say, this is basically liquid to solid. So this curve will be something like as this temperature is the freezing temperature, which we call as TF. So we'll draw such curves, and we'll try to understand how the free energy of the system, which is the Gibbs free energy, is changing with temperature as well as with pressure. And then we'll talk about the phase transition for one component system. And after that we'll consider, we'll discuss about chemical equilibrium, and then we'll consider discuss some part of electrochemistry, and there we'll conclude our part on the lectures on thermodynamics portion, and then we'll discuss we'll start the discussion on the chemical kinetics. Thank you.